Hello, I'm Suzanne Menzel. In this video, I'm going to tell you how I applied the 7 steps of the Decoding the Discipline cycle to my class, Introduction to Computer Science. The first step in the Decoding the Discipline cycle is to identify the bottleneck in your class. For me, this was easy. My class is all about recursion, and so I picked recursion as my topic. Recursion is a way of thinking about data and programs and how they interact. And it is transformative in the sense that it changes the way a student views computation. It integrates previously understood concepts that students understand very well into something that is new, different, and surprising. It's irreversible in the sense that once they learn how to do it and they internalize it, it's like riding a bike. You don't forget it. And it troubles them. They find it very difficult, surprising, and they resist it. And they just don't believe that it works. So in this sense, it is a threshold concept, not just for my class, but for all of computer science. It's an extremely important topic. So it was really good bottleneck to start off my cycle. Like Alice through the looking glass, the students must pass through this cycle in order to progress and understand and grow in the course. Step 2 of the cycle involves an interview process designed to uncover those features of the bottleneck that you, the expert, have encoded and internalized. The process of unpacking your tacit knowledge during the interview gives you a deeper understanding of the student experience because the interviewer is trained to verbalize their thinking and challenge your explanations. Recursion can be explained in 2 ways, as a structure and as a process. A physical structure is recursive if one of its parts looks like the whole. In this example of a data structure, I've made something with 2 fields, x and y. But inside the x field, there's just a number. Inside the y field, there's something that looks like the whole. It itself has an x and a y field. And we continue this by placing the same structure into the y field until we have to stop at some point. I stop with the number 1 here. There's an analogy to be made here with a Russian nesting doll. Here, the inner dolls, they look like the whole. And this is a physical thing that students can see, understand, they can hold it in their hands. The process, however, is not as straightforward to understand for the student. They have a particularly hard time accepting this notion. It's a different story when it comes to procedural recursion. This is when the student expresses an algorithm in terms of recursion, and this is the foreign concept, the one that their minds resist. They have a hard time believing and trusting that it works and will lead to a correct solution. So this was my epiphany. I need to put more weight on the process of recursion, and like the physical metaphor for the structure, I need a physical metaphor for the process. One obvious way to do this is to have the students act out the execution of a recursive algorithm. What you see here is a fast way of collecting attendance cards from the students. You see they're all active, up, and engaged. It's fast because there are multiple collectors in play, they're in action, not just one person collecting while others sit idly by. Here, the students are executing an algorithm to count the total number of dolls that make up a Russian nesting doll. We see them repacking the dolls and using the computed result, which in this case is a number. They're writing it on a card, they're handing it back to whoever called them in the first place, and they're going back up through the recursion call stack, assembling the data, passing it back up, until finally we get back to the caller, and we see that in this particular sequence of Russian nesting dolls, there are 10 of them. This is returned to the initial caller, who has the answer, and there they are. That's fine for introducing the concept, but recursion is pervasive throughout the course. It morphs and evolves as the problems we try to solve become more complex. For a threshold concept, you really need systemic interventions to explicitly model your thought processes for the students throughout, not just a one-shot deal. And this leads us to step 3 of our cycle. We want to choose well-supported, research-based methods to help students develop more robust understandings. I decided on 2 interventions. The first is an extension of code reviews, which is something that I had long done in my class. Students would work in groups of 2 to write code on index cards during class, and I had mechanisms in place to ensure that each team member contributed equally. On this card, Josh and Amy are taking turns writing lines of code, and you can see that by the different writing implements they used. Students would submit their work to me, I would project the work and do a code review of the class so they could see how I thought about the code. I expanded upon this idea greatly and implemented a strategy called team-based learning, TBL. It's popularized by Larry Michelson. I created persistent groups throughout the semester of 4 to 7 students. I would give them short reading assignments from a text that I'm about to explain. And to ensure that they were prepared, there was a readiness assurance test at the beginning of the lecture. And this happened about every 3rd lecture. The students would come to class with the requisite background knowledge, and that freed us up to use the class time to work in the larger groups. The result was that students felt answerable to their team members, not just me. Once you decide on an initiative, you need the courage to put it into practice, and this is indeed a bit scary at first. Here are some pictures of my students working together in the TBL groups. This can be done successfully even in a traditional classroom. Students will just have to get up and move around a bit. In this particular room, the chairs are arranged in rows and nailed to the ground, but I was still successful in getting a lot of active teamwork during my class. My second intervention involved switching to a top-down, algorithm-centered approach to teaching programming. I adopted this book by John McCormick. It's a popular press book. It's not a textbook, really. He describes 9 algorithms that people use every day, things like performing a Google search or transferring money securely, electronically, or downloading music without losing any information. By focusing on the algorithms, we motivate the programming, and we're able to explore the ideas of the world of ideas, not just the minutiae of syntax, which leads us directly into step 5 of our cycle. How the algorithms work is intriguing and surprising and motivates the students. Students begin work in their TBL teams on an algorithm. Here are some examples. They continue in the lab section, and then they implement further ideas on the homework, and it becomes a very integrated package. How do you evaluate whether or not the student has mastered the material? Well, for us, this didn't really change. We did this and continue to do this, and have always done this with 2 exams, a midterm and a final. In order to figure out if we're making an impact, we conducted a study of 426 students. 236 had taken the course over the previous 3 semesters. 190 took the course using our 9 algorithms approach. Not everyone received the TBL treatment. So in this talk, I'm going to focus here on the 9 algorithms intervention. A little bit about the final exam. For this course, our final exam has had a stable format for about 15 years. The majority of the exam involves writing code, either on paper or the computer. We always release the prior exams to the students, and we never repeat problems. Every exam has 2 classic problems. There is always a list recursion problem and always a tree recursion problem. The students know this, they see examples, they're warned of this, these are our baselines. We also grade in a consistent and reliable manner. The grading is anonymous. We use a letter grade scale, 23 points. Here's the connections. And you can see that 12 is a passing over here, and a B is about 19. So we use this 23-point scale. Okay, so I'd like to share with you in the last step of the cycle what worked and what doesn't work. That's what I'm doing right now. The main result here is, first, there's no difference in the preparation of our students in the pre and post groups as measured by our SAT or our college entrance exam. So the populations are comparable. And the main thing is that for the post-9 algorithms group, they perform significantly better on both the list recursion and the tree recursion problem. And I will show you our graphs. So here is the data for the pre-group, 236 students, and you can see that the students are falling in the B range on average. And in the post-group, we have an improvement here from a grade of B to a grade of A-. That's statistically significant. In the tree recursion problem, this is what the graph looks like. Tree recursion is a little harder than list recursion because there are 2 recursive steps. And this is what the graph looks like before, and then after we are able to shift it to this. So we get from a C average to a B- average, statistically significant. We also administered a survey of our students shortly after the midterm. I'll share with you some of their comments, although the emphasis is mine, but you can see that they really enjoyed this. They realized that they were being trained to think like a programmer and not just a code monkey. That they saw that the thinking was important and the syntax was not. They felt a sense of accomplishment. They enjoyed working in teams, which was very gratifying, and they saw this as a challenge that it taught them to think in a new way. And I'll leave you here with a picture of me and my students, the next generation of computer scientists. Thank you.